Welcome back to this course on blockchain and its applications. So, in the last class we have looked into the crash fault tolerant architecture, and we have seen that how we can achieve consensus in a CFT environment in the presence of asynchronous communication channel. So, we have seen the broad idea and we have seen basics about Paxos. So, today we are going to look into these algorithmic aspects of Paxos in details. So, that is the concept which we are going to cover today, Paxos in the context of CFT consensus, and the corresponding keywords are Paxos and CFT. So, to start with Paxos, Paxos considers different roles for individuals. So, in the last lecture we have seen this particular example where I mentioned that you and many of your friends are going to decide about something after this lecture is over, and let us see that how Paxos assign the roles on individuals on this kind of message passing architecture. So, here you see that two of your friends or maybe one of you, you have made certain kind of proposals. So, one proposed about going for a dinner and another one proposed going for a movie. Well, so Paxos called them as the proposer. Well, and then there are other nodes, other persons in the system who are going to accept one of the proposals. So Paxos called them as the acceptors. Well, so these are the kind of two broad roles that individuals have. They can be a proposer or they can be an acceptor. Now, interestingly here for this particular guy, what we see that this guy had initially made a proposal for dinner, but when another guy had made a proposal for movie, this guy had agreed on that movie. So, it has accepted this proposal of movie. So, this guy has actually a kind of dual role. So, this guy is working like a proposer as well as a acceptor. Well, so that way a proposer can also be an acceptor in Paxos. There is a third role which is there. So, this third role we call it as the learner. So, what is a learner? A learner basically means that whenever you are going to reach to a consensus, then this learner nodes, they are going to learn that what is the value at the consensus is. Well, so for example, ultimately you agreed to go for a movie. So, movie is something that you have agreed upon at consensus. So, the learner nodes, they are going to learn that well certain consensus algorithm has been executed in the system, and after execution of that consensus algorithm, collectively we decided about going for a movie. So, that is the purpose of the learner. So, that way there are three different roles: proposer, acceptor and learner. And as I mentioned that any node can have any or all three of these roles. Well, now the interesting fact is that these nodes must know how many acceptors a majority is. Well, for example, here in this case I have 5 acceptors, that means the majority is 3. Well, so that information Paxos assumes that that is known a priori. So, you know that how many acceptors are there in the system, and when you know that how many acceptors are there in the system, you can decide that well what is the majority. Well, so if there are 5 guys, 5 acceptors, so you can decide that well 3 is the majority. And why do we need that? Why do we need that information? Because if there are 2 different majorities, then that 2 different majorities always overlap in at least one node. What does it mean? See, you had 2 different proposals, one is for movie, another one is for dinner, and you have 5 nodes. Now, if you say that well majority is dinner, that means there are 3 nodes who should accept dinner. Well, or if you say that say movie is the majority, then again there should be at least 3 nodes who should accept on the movie. Well, now here you have a conflict if I apply pigeonhole principle, because it can never happen that movie is majority and at the same time this dinner is the majority, because if movie is the majority I have 3 nodes, then if dinner is the majority I have 3 nodes. but total I know that I have 5 nodes, that means there is one node in common who will either agree for movie or agree for dinner. So, if that guy agree for movie, then movie becomes the majority. If that guy agree for dinner, then dinner becomes the majority. Well, so that way if you have 2 majority, the condition of the majority is that these 2 majorities will always overlap in at least one node. Why does we have this constant? Because if you have 5 nodes, it is much more easier, but assume that if you have 6 nodes, then what is the majority? So, if you have 6 nodes, then 3 is not the majority. Why that is not so? Because if you think of that or 3 is the majority, then you can have 3 nodes which are accepting one thing and 3 other nodes which are accepting a different thing. Well, so then I do not have any common between these two. So, that way 3 cannot be a majority when your number of acceptors are 6. So, what can be a majority? 4 can be a majority, because if I say that 4 is a majority, then I can guarantee that, well, if there are 4 nodes this side, if there are 4 nodes that side, then there are 2 nodes which are in common. Well, so that way the majority is defined, and we accept a particular proposal based on majority voting. And again I am repeating, because we are considering that CFT consensus, in the CFT consensus only crash can happen. So, that means you will either receive a message or you will not receive it. Well, it will never happen that you will receive 2 different messages from 2 different guys. Well, that will never happen. If that happens, that is the second type of fault, which is the Byzantine fault, which we will discuss later on, okay, which we are not going to discuss here. So, in this context, either you are going to receive the correct message or you are going to receive none. We are at a CFT consensus environment. Now, in this CFT consensus environment, if I just try to look into that how Paxos works. So, as I mentioned earlier, that Paxos is based on state machine replication. So, these proposers and the acceptors, they maintain a state of the running epoch. What is meant by running epoch we are going to see later, but in summary, this epoch basically means one unique variable which is represented as IDP, where p is an epoch number. Well, so p is an epoch number that actually maintains the state, and what I need to ensure that p is unique across the system. So, you can design p in different way. You can think of that, well, your system time represented in the Unix epoch time, that becomes your epoch number, but this p value of p need to be unique across different messages which are coming. Now, a Paxos run, it aims at reaching a single consensus. That means, you have the problem of consensus, you run Paxos, well, and you reach to a consensus and it ends there. Well, if you say that I want to reach into multiple consensus in multiple different rounds, that you cannot do by a simple Paxos. What you have to do, you have to run Paxos multiple times. You need to run Paxos in rounds. So, that we call as the multi-Paxos. So, we will see multi-Paxos later on, but for the time being, what we see that, well, the system is currently starts with a set of states. Well, then we run Paxos, and once they reach consensus, they reach to a final state, and this final state is something from where none of the node will be able to deviate. Well, so that way Paxos is connected with the state machine replication problem. Okay. In this context, again I am repeating that I will have certain initial state S I. Well, so I run Paxos and I reach to a final state at consensus. So, what this final state is something where every correct node will reach and they will not be able to deviate from this final state SF. Well, so that Paxos ensures that once you are reaching to a consensus state, you will not be able to deviate from that state. Now, let us see that how Paxos works. So, we consider about a single proposer initially, and assume that we have a single proposer and we have multiple acceptors. So, assume there are 3 acceptors. Well, so there are 3 acceptors, that means 2 is the majority. So, Paxos starts in this way. So, in Paxos, the proposer wants to propose its choice, that we call as the value. Now, to propose that value, the proposer sends a prepare message with certain ID to a majority or all of the acceptors. Well, so what the proposer does? Proposer sends this prepare message, assume that this IDP is 100. Well, so as I mentioned that this number need to be unique. Well, so it should not happen that two prepare message with the same ID number, same number 100 is generated by multiple different proposers. That should not occur. This number need to be unique across different proposers. So, the proposer sent a prepare message with this unique ID. Now, once this is received, well, and as I mentioned earlier that this IDP must be unique across proposers for each prepare message. So, you can have different way to generate this ID. You can use directly the timestamp, or you can use a hash of the timestamp and the proposer ID to generate this unique ID. So, once you are generating this unique ID, then you are sending, the proposer is sending a prepare message with this unique ID. Say here we have received prepare 100. Now, the acceptor it's received a prepare message with this ID. So, when an acceptor received a prepare message with an ID, so the acceptor checks that whether it promised to ignore the request with this ID. What is mean by promise? Promise means that whenever the acceptor does certain promise, it is going to send that message. So, we are going to see. So, if the acceptor has promised to ignore the request with this ID, then you ignore this message. Otherwise, you will promise to ignore any request lower than ID. Okay? So, this is important. So, if you receive a prepare message with certain ID and you see that you have never promised to ignore message with this ID, then as an acceptor you will promise to ignore any request lower than this ID. That means, if after accepting or after promising with prepare with 100, if another promise comes with another prepare comes with 50 or 55, then you are going to ignore them. Well, so if you do not want to ignore 100, or if you have not promised to ignore 100, then what we are going to do? You are going to reply with a promise message with this particular ID. So, the acceptors will send the promise message. So, when the acceptor is sending this promise message to the proposer, that means the acceptors are agreeing that, well, if another prepare message comes which is having the IDP lower than 100, then we are going to ignore that. Well, now here I have put up a question mark. So, we are later on going to add something here. So, what we are going to add something here, we will see it later on, but for the time being just assume that whenever you are receiving a prepare message as an acceptor, if you have promised earlier to ignore this, then you ignore it. Otherwise, you send a promise message with that particular ID, here with promise 100. Now, once you send that promise message, then if majority of the acceptors promise, then no ID less than IDP can pass the protocol. Well, so this is again interesting in the context of Paxos, because if you see that, well, majority of the acceptors have agreed that we are going to ignore anything less than 100, that basically means if any other prepare message comes something less than 100, that will never be able to make any progress in Paxos. Well, that will be ignored by all the acceptors or majority of the acceptors. Well, so that basically means that the acceptors here agree on a state 100. Okay. So, this is again important to note that as I mentioned earlier that Paxos is based on state machine replication, and here comes the notion of state, That means you are deciding the state of the system and you are saying that well, with this state of the system we can always make progress, we are never going to look back. That basically means that well, I have agreed on state 100. So, if something comes from state 50 or state 55 or state 95, I am going to ignore that. Well, if something comes that make this state to progress further, then I am going to look into that in details. Well, so that is the agreement which is happening here by exchanging this prepare message and the promise message, where the proposer is saying that well, I am proposing to move to the state 100, and the acceptors, when they say or when they see that well, they have not promised earlier to ignore this particular state. So, they say that well, we also agree to go with this particular state which is state 100. Well, so they agree on a current state value. So, once they agree on that current state value, now let us see that what happens next. So, next once the proposer gets majority of the promise message for a specific IDP, the proposer now sends this accept request with IDP and certain value to a majority or all of the acceptors. Well, and it picks a value of its choice. So, here again we put up a question mark, we are going to add something here later on. What we are going to add later on we will see later. But for the time being, you just assume that whenever a particular proposer it receives promise from multiple acceptors saying that the acceptors agree to move ahead with state 100, then that particular proposer sends this accept request message, and this accept request message contains a parameter value, and this parameter is something on which we are going to reach consensus upon. Well, so remember that consensus is not on the state, the consensus is on the value that is being proposed. Well, the state is just to ensure that we are always making progress in receiving the message, and if certain message gets delayed, say for example, it might always happen that certain prepare message that have been sent by another proposer long back and we are in an asynchronous system, that message get delayed and that message comes later on. Well, so the proposer might have sent one say prepare message long back with say prepare 100 with say prepare 50, and that message now gets received here. Well, so we are in an asynchronous system, that might happen because messages might have arbitrary delay. And what we are doing with this state variable, that this particular notion of the asynchronous environment, that we are putting up a wall here saying that such kind of delayed message we are going to ignore. Well, so if certain message gets delayed because of this asynchronous communication nature of the channel, we are going to ignore it. So, we are going to ignore this message which says that prepare with value 50, because we have passed that state and we are at a state 100. Well, if something newer comes, we are going to look into that, but we are not going to look something old. So, that way the state variable is actually ensuring me or ensuring handling of this asynchronous communication environment by providing an wall to the older messages that have been sent earlier that have possibly been delayed due to the asynchronous nature of the environment. Well, but we are not going to reach on the state, as I mentioned, that we are going to reach consensus on the value, and this is the value which is being proposed by this proposer. Well, so once the proposer sees that well, the acceptors are agreeing on the state, well, that means the proposed prepare message that I have sent, that message have not seen any large arbitrary delay and no one else have proposed in between. It is not like that I have said that let us go for a dinner, and that message has not been received by others, and someone else have said that let us go for a movie, and people are now discussing about the movie. So, those things we are taking care of with the help of this state variable. Well, and once the proposer sees that well, it is the case that the acceptors are relying on me, the acceptors are agreeing that well, they are going to hear me, then the proposer is again sending this value with this accept request message. So, the next message that is going to pass is this accept request message. Here with this accept request message you send the value which is the dinner, okay, and with the same IDP number. Now, in this way when the accept requests are being propagated, the acceptors receive an accept request message. When the acceptors receive an accept request message, the acceptor checks again that did it promise to ignore request with this ID. Well, if yes, if it is a kind of again delayed message or something, they have already moved to a new state which is more than that previous state, they are going to ignore this. Well, otherwise they are going to reply with an accept message with the corresponding ID and the value, and this information is also sent to all the learners. So, what is happening here? So, the accept message is being propagated from the acceptors to the proposer, and the learners are also getting that accept message. Well, and when this accept message is being sent, the accept message basically says that we are reaching consensus on this value dinner. Well, so if majority of the acceptors accept IDP value, then consensus is reached, and again I am repeating that the consensus is reached on the value, not on the state, okay, because the state might progress further. We will see that the state might progress further, but once majority have accepted a value, majority have agreed upon a value, even if the states gets progressed, the value does not get changed. Okay. So, it is something like that. If you remember that example I mentioned earlier, that one of your friend earlier, that friend has accepted dinner, and then the friend thought of that, well, we are going for the dinner at 9 p.m. So, I have 2 hours in hand, let me go for a short sleep, and by that time when the friend was sleeping, other friends they have came to a consensus on a different value. Okay. And when that friend woke up, the friend sends a message and found out that, well, dinner was something old and they have moved to a new value. So, the state thing is maintaining such kind of stuff. The state is ensuring that, well, you can propagate the states, you can proceed with the states, well, but once you agree to a value, you does not make any change in that value. Well, now how you are going to ensure that? Well, here comes my notion. So, if you remember that while discussing about this algorithm, in few places I have put up these question marks. Now, we are going to fill up that question marks with the case when Paxos is going to execute for multiple different proposers. So, before going to that, when as I mentioned that when the proposer or learner gets this accept message with IDP or value, if the proposer or learner gets majority of the accept for a specific IDP, they know that consensus is reached for that value. Well, so we have reached consensus on dinner. Now comes that scenario. Well, so I have multiple proposers. So, assume that it happened that the acceptors have already sent this accept message, well, with ID 100 and with a value as dinner, and now this proposer is going to send another proposer, say this is proposer 1, this is proposer 2. So, this proposer 2 is going to send another prepare message with value 50. Well, now what will happen here? So, let us revisit our algorithm. So, our algorithm says that this acceptor it will the acceptor it will receive a prepare message, and when the acceptor will receive a prepare message with certain ID, it will see whether it had promised to ignore that request or not. If it promised to ignore that request, then it will ignore, otherwise it will send a promise message. But whenever we seen earlier that there was a prepare message with ID 50, but you have already promised to ignore something less than 50, you agreed on 100. So, this message will get ignored. But although this message get ignored, the proposer may send another prepare message with a higher value, that is say 150. Now, when this proposer is going to send another message with a higher value with 150, then we add up this additional things here that we see whether it ever accepted anything. Okay. So, here is the thing. So, earlier you have already accepted on certain value, and after you have accepted on certain value, a different proposer is sending another prepare message, possibly with a higher state. But what you need to ensure that because you have already accepted dinner, you are not going to deviate from dinner. Well, so that condition we are going to add here. So, if you have ever accepted anything, that means if your reply is yes, then you reply with promise IDP accepted IDA value. Okay. So, you send that, well, you have sent the prepare message which has a higher state number. So, let us move with that state number, let us have promise with 150, but there is a but. What is that? That we have already accepted our value. Okay. So, that information you are sending to the proposer, you are sending to the proposer saying that, hey, at state 100 we have already accepted our dinner. Well, so you missed that and you are sending a new proposal. So, you have no other way to rely on dinner, you cannot deceive the consensus from there. Well, so that is the information which the acceptor is going to send. And again I am repeating here that we are talking about the CFT consensus, we are not talking about the Byzantine behavior here, because we are not talking about the Byzantine behavior here, we are only assuming that a crash can happen. Okay. Nodes are not going to send any wrong message. So, what happens when nodes are going to send wrong messages, that we are going to see in the later on classes. Well, but for the time being, because this proposer is also a good proposer, well, it is not a Byzantine proposer, only crash fault can happen. So, if someone says that, hey, you have sent some new state that is good, but we have already accepted on some value, then the proposer will actually respect this consensus. And what will happen next? That next the proposer, when it gets majority of such promise message for a specific IDP, well, earlier we have seen that it sends an accept request with a value to the majority of the acceptors, and we said earlier that it can pick any value it wants. Now, this particular condition we are going to change, it is not any value it wants, we would see that whether this promise already contains some value or not. Well, and when promise already contains some value, the proposer is going to respect that information. Well, and what the proposer is going to do here, this is the new addition here, this part, that proposer checks that has it got any already accepted value from promises. If yes, you pick that value with the highest ID, if no, you pick the value of its choice. So, if the promise message contains a value, you pick up that value. If the promise message does not contain any value, then you tell about your proposal, your value. Okay. So, this is something again, means what you see, that before proposing something, you see whether the acceptors have already accepted on something or not. Well, so it might happen that what proposer 1 has proposed, you have not received that, because you are in an asynchronous channel. Well, and because you have not received that, so that is why you rely on that information. So, whenever you are going to propose something, well, you send that prepare message, and if the acceptors have already accepted some values, or if majority of the acceptors have accepted some values, you are going to get majority of the promise message with that value embedded. So, from that information you get to know that, well, the acceptors have already accepted something. So, you cannot deceive from that value. Well, so if this particular scenario occur, then it sends the accept request with that value only. So, it will not deceive from that value, it will send the accept request message for dinner itself. Well, and the protocol progress in that same way. Well, so because we are not changing this particular dinner thing, so it will go with dinner. So, what we see here, that this Paxos gives a nice construction. So, it is basically a kind of works in 2 rounds. So, in the first round we are making an agreement on the state with the help of this ID, and then we are making an agreement on the value. And this synchronization among the state and a value that is helping me to handle the asynchronous behavior of the network. So, even if you are getting delayed message, if the system has progressed to a higher state, you are going to ignore it. Okay? If it happens that you have not heard of something, but acceptors have already accepted an value, whenever you are going to send a new prepare message, you are going to hear back that value from the majority of the acceptors, and whenever you are going to hear back that value from the majority of the acceptors, you know that this is the value on which the acceptors have already agreed upon. Okay. So, there is already an agreement among the acceptors on that value. So, that value is the value at the consensus. Well, so this is the kind of broad Paxos algorithm, and in the next class we are going to discuss about the safety and the liveness property of Paxos. Well, and we are going to see that what happens when we try to deceive from safety or we try to deceive from liveness, and how with the help of this majority voting Paxos is going to prevent those kind of behavior. So, thank you all for attending today's lecture. See you all in the next lecture.